Good morning, fellow mathematicians. Welcome back to another video. Just like announced in the community tab here on YouTube, I want to give Ahmed's integral another shot because one day I pretty much woke up and I thought about Coxetter's integral, so the climax of the last random week, and a thought came to my mind on how to solve this right here. And it was quite a problem at some point. I'm going to talk about this in a few minutes. We are going to dive right in because this is going to take a while, I guess. So, what do I want to do basically? Well, I would like to turn this into a double integral using just the identity for the inverse tangent. So, if you remember correctly, if we have 1 over a times the inverse tangent of 1 over a, well, this is nothing but this right here, inverse tangent x over a, from 0 to 1 basically. And this is nothing but the integral from 0 to 1 of dx over x squared plus a squared. We don't want this a to be equal to 0, so we can multiply both sides by a right here to be left with this identity right here for the inverse tangent. And we want to interpret this right here as just a 1 over a term. So you can interpret this as 1 over square root blah blah blah. And now we can turn this inverse tangent into an integral basically. And with respect to a new variable, for example t, I really don't care. So at first we have the integral from 0 to 1 of 1 over x squared plus 1 times square root x squared plus 2. What else do we have? Well, this right here is the 1 over term, but we are going to take it 1 over 1 over. So 1 over square root x squared plus 2. Just write it out basically. And then times the integral from 0 to 1. This time with respect to t, the upper and lower bounds and the integral in itself. So we have this, and we also have this dt over t squared plus, and now 1 over this right here, squared. So 1 over x squared plus 2 integrated with respect to x. What I want to do now is combine those two to get rid of the square root, you could say. And also I would like to factor out this 1 over x squared plus 2. Then we have 1 over x squared plus 2, taking the reciprocal, bringing this up. So we end up with an integral from 0 to 1. I'm going to bring this integral to the front, integral 0 to 1. And now we have 1 over x squared plus 1 times x squared plus 2. You see, this is just this combined right here. And now we have 1 over x squared plus 2, but this is going to be nothing but x squared plus 2, basically cancelling out with this one. So this and that is going to cancel out overall, and we have 1 over. Don't forget, we are bringing this to the outside, so we have a 1 right here, but also we have this term, so t squared times x squared plus 2. So this is just t squared times x squared plus 2 plus this 1 right here. Integrated with respect to t, integrated with respect to x at the moment. What I would like to do now is to just multiply this out right here a little bit, factor stuff out, and also I would just like to interchange those integrals right here. Integrating with respect to x at first and then with respect to t after that. So that's what I would like to do. I can't really tell you why I can do this. I'm the papa, so I'm just going to interchange those integrals right here. So we are going to end up with an integral with respect to t running from 0 to 1. Integral with respect to x running from 0 to 1. And now we have 1 over x squared plus 1. Let's put it that way. Times 1 over t squared times x squared, and I'm going to put it like this, plus 2 times t squared plus 1, but in parentheses, dx dt. And this right here is exactly a job for partial fraction decomposition, so I'm going to do this in a little outtake. After doing the partial fraction decomposition, I've written everything out once again and just factored out this term they had in common basically. And well, now we can continue with this. Just watch the outtake. You see, this right here is easy to evaluate. This is nothing but the inverse tangent of x from 0 to 1. Inverse tangent of 0 is just 0. Inverse tangent of 1, you can calculate it by hand whatsoever, is going to evaluate to pi over 4, if I'm not mistaken. I hope I'm not mistaken. Okay, now we have this right here, and we want to bring it into the form of this one. So, yeah, how could we do that? Well, we could factor out the t squared term on both terms. That means over t squared. That's going to cancel out, bring it to the outside. Same spiel here. And you see, now we have x squared plus something. But in order for us to get this arctan, this inverse tangent identity, we have to have 1 over x squared plus something squared. So why not take the square root of this term right here and just square it once again. That's also going to cancel out to 1. So let's just gather what we've got. So this right here is now nothing but the integral from 0 to 1 of dx over x squared plus square root 2 times t squared plus 1 over t squared. Yeah. That's basically it. And this is now nothing but the inverse tangent of some sort. So this is going to evaluate to the reciprocal of this thing right here. So square root t squared over something. Square root of t squared is the absolute value of t. But we are integrating from 0 to 1 right here. So it's always positive, so it's just regular t. So t over square root 2 times t squared plus 1. Okay, coolio. And also times the inverse tangent of, and now we have x over this thing right here. So x times t over square root 2 times t squared plus 1. Integrated from 0 to 1 once again. Inverse tangent of 0 is 0, so this is going to vanish completely. Inverse tangent of 1 in this case is just going to leave us with this chunk right here. So this overall, I'm going to write it here, is going to evaluate to an integral from 0 to 1. 1 over t squared plus 1 times big brackets pi over 4 and then negative, don't forget your negative sign, t over square root 2 times t squared plus 1 times the inverse tangent of t over square root 2 times t squared plus 1. Here, integrated with respect to t. That's a lot of work, a lot of writing. And now we can just use the linearity of the integral to break this up into two integrals. Let's write everything out. Also, I called the original integral a for Ahmed's integral, just for clarification purposes. Okay, there we go, and this should seem quite familiar to you at the moment, because that's basically what we've got the last time we've evaluated Ahmed's integral. This right here is going to evaluate to pi over 4 times the inverse tangent of t from 0 to 1, which is nothing but pi over 4 once again, so pi over 4 times pi over 4 is nothing but pi squared over 16. Okay, coolio, but what the hell is this right here? Well, last time we've introduced the substitution, t being equal to, I don't know, 1 over u, for example. So let t be equal to 1 over u. That also means that dt is nothing but negative 1 over u squared du. And we can plug this information into here. That means now we have pi squared over 16 negative. Okay, lower bound 0. This only happens if u goes to infinity in the limit. And upper bound 1, well, this only happens if u is 1. So we have an integral from infinity to 1 at the moment, and now let's plug in all the values for our t. So 1 over u up here over 1 over u squared plus 1 square root 2 over u squared plus 1 inverse tangent of 1 over u square root 2 over u squared plus 1. And also we have this right here, negative 1 over u squared du. What we can do now, we can distribute this negative sign into here to change the upper and lower bounds, respectively. And also, we can factor out a 1 over u squared term in here, and also we can factor out the square root 1 over u squared in here, making it the absolute value of 1 over u, but the thing is, positive interval, meaning the absolute value is just the value itself. Same thing here, and a lot of stuff is going to cancel out. Watch the original Ahmed's integral to just follow all those steps. So we have pi squared over 16 negative integral from 1 to infinity of. So we have this 1 over u squared term factored out, but it's going to cancel out with this right here. So this gets rid of this. Also we have this right here cancelling out with this. Same thing in here. So we end up with du. No, I'm going to bring the du to here. So we have the inverse tangent of. This is now nothing but 1 over square root 2 plus u squared. And down here we have 1 plus u squared, square root 2 plus u squared. Yeah, this should be basically it. And here's the thing. That's not what we've got the last time, because the last time what we had was just Ahmed's integral in itself once again. And this wasn't problematic in the least bit, so this was quite easy to evaluate. But this time we have this abomination right here from 1 to infinity. And I tell you something, if you use the same techniques we have used right here, it's just going to be a fucking mess, because you are going to end up in a circular argument. You are just going to end here once again, and you are just going to be left with 0 being equal to 0. And this doesn't help in the least bit. You know, Ahmed's integral is going to evaluate to 5 times pi squared over 96. Meaning we have this chunk right here minus, well, this right here in the end. And also we are going to use a trick in a second with this inverse tension identity. Yeah. That means this right here is going to have a finite value, because Ahmed's integral is finite. Finite plus finite is going to end us up with something finite. Just keep this in mind. So that means this integral is going to converge in the end. That was my train of thought. I'm going to tell you in a second how we are going to proceed. At first, let us rewrite this a little bit, because we know that the inverse tangent of x plus the inverse tangent of 1 over x is nothing but pi over 2 if our interval is completely positive. We can rearrange this a little bit, because we have the inverse tangent of 1 over something. That also means that the inverse tangent of 1 over something is nothing but pi over 2 minus the inverse tangent of this something. We can plug this new information into here. Using the linearity of the integral, we can break this up a little bit. Pi squared over 16 minus, now we have this pi over 2 times the integral from 1 to infinity of just du over 1 plus u squared, square root 2 plus u squared. And also basically Ahmed's integral, but with changed upper and lower bounds. So negative and negative becomes positive. So positive integral 1 to infinity of inverse tangent of square root 2 plus u squared over 1 plus u squared, square root 2 plus u squared du. Sorry for the sweet little jump cut. Timo just came in getting himself some coffee as always. I did want to make a little cut anyway. So you see, this right here is just like Ahmed's integral, but with changed upper and lower bounds. And this right here is something we can easily evaluate. This is the small snack. I'm going to talk about this in the end. Like I said, when you deal with this one, using this technique, you are going to end up in the circular argument, because you are always going to end up with this 1 to infinity stuff. So what I thought is, well, Ahmed's integral goes from 0 to 1 with this integrand, and this one right here goes from 1 to infinity with this integrand. So why not use the linearity of the integral to bring those together to an integral from 0 to infinity with this integrand? And that's what we are going to evaluate next, to find out the value of this thing right here, ending up with a little system of equations basically. So here's my train of thought. We have this right here now, with this thing being the one in question. So we can just in the end solve for this one right here. And what you do, basically, just pause and ponder, try it out for yourself. You go through the same process with the double integral, with this new integral that we want to evaluate right now, up to this point. So just doing all the same steps, it's nothing new, it's just the same thing. And you see, what we are going to end up with now is this chunk right here. With this evaluating to the inverse tangent of x from 0 to infinity. And I believe in you guys, I believe that you can just fill the steps in right here, little exercise for the viewer. So inverse tangent of 0 is just 0, inverse tangent when x approaches infinity is just pi over 2. So this is going to evaluate to pi over 2. And this thing right here, just like before, is going to evaluate to this chunk times the inverse tangent of this chunk reciprocal stuff. But this time from 0 to infinity. So this right here is nothing but t over square root 2 times t squared plus 1 inverse tangent of, and now we have t times x over square root 2 times t squared plus 1 from 0 to infinity. And you see, if we evaluate this at 0, this is just going to vanish. If we evaluate this at infinity, and this is the really cool thing, this inverse tangent is going to be pi over 2. So we are going to get rid of this inverse tangent. This is just doing the trick so nicely. And you see, t is going to be finite from 0 to 1, so it doesn't really matter if you have this shit right here. It's just going to evaluate to pi over 2 in the end. So this right here is nothing but pi over 2 times t over square root 2 times t squared plus 1. Yeah, and now we can just combine all the stuff. So we end up with, now we have an integral from 0 to 1. This is pi over 2, using the linearity of the integral, breaking stuff up. 1 over t squared plus 1, let's put a dt right here. And we also have negative pi over 2 integral from 0 to 1 of, and now we have dt, so t times dt, because we have this t right here. We have t squared plus 1 square root 2 times t squared plus 1. Yeah, this is basically it. Let's bring this little dt right here, and we know how to integrate this right here. So this in itself is really quite easy. It's from 0 to 1, so we know what this is. This is pi over 2 times, well, inverse tangent of 0 is just 0, inverse tangent of 1 is pi over 4, times pi over 4 being just pi squared over 8 in this case. So what is this right here? Well, let us introduce a new substitution. Let this square root stuff right here, square root 2 times t squared plus 1, be nothing but u, for example. That also means, if we differentiate this, that the u is nothing but. So I'm not going to write this out, it's really quite easy. We have done this before so many times. So this is 1 over, and now we have 2 square root 2 times t squared plus 1. Taking the inner derivative of this thing is going to leave us with 4 times t. This 4 and this 2 is going to cancel out somehow. We are going to end up with this. Dividing both sides by 2, because it's not equal to 0, it's going to leave us with this. So this chunk right here, don't forget your dt, is nothing but du over 2. So this right here is negative pi over 2. And now we have integral from, yeah, let's see. So we have 0 right here. This is going to evaluate to just 1. And we have a 1 right here, so this is square root of 3. I hope you can manage. I'm sorry if this feels a bit rushed, but I just want to go through this whole process pretty quickly. Okay, what do we have? So this is just, we can bring this 1/2 to the outside, so pi over 4 in this case, and we have du over t squared plus 1. Here's a big question. What exactly is t squared plus 1? Well, why not just solve for our t squared a little bit? So we can square both sides. That means that here, u squared is nothing but 2 times t squared plus 1. We can subtract the 1 on both sides, and also we can divide both sides by 2, leaving us with u squared minus 1 over 2 being nothing but t squared. We can plug this stuff into here, actually. So we end up with negative pi over 4, integral from 1 to square root of 3 du over u squared minus 1 over 2 plus 1. We can factor out the 1/2 on both terms, then we have to take the reciprocal, getting rid of this 4 once again. So we end up with pi over 2, integral from 1 to square root of 3. Then we have a du. This is going to turn into a 2. 2 minus 1 is just 1. So u squared plus 1. And this is nothing but the inverse tangent. So this is pi over 2. Negative pi over 2 in this case. Don't forget your negative signs. Negative pi over 2. Inverse tangent of u from 1 to square root of 3. inverse tangent of square root of 3 is pi over 3, if I remember correctly. I hope that's correct. So that's negative pi over 2. And then we have just, inverse tangent of square root of 3 is pi over 3 minus pi over 4 in this case. We can advance those fractions to a 12 down here. So this is 3, this is 4, so this is 1/12, pi over 12 you could say. So this is negative pi squared over 24. Yeah, and this is basically it. So we have found out what the value actually is of this thing right here. So this was really easy to evaluate. So you know, this is now nothing but pi squared over 8 in this case, minus pi squared over 24, if I'm not mistaken. We can advance this fraction by 3 over 3, and 3 over 3, so to get a 24 right here. So this is just pi squared over 12. And the cool thing is now we can solve for this integral right here, which is really, really cool. So this also means, in conclusion, that this integral, 1 to infinity, f of x dx, that's an equivalence, is equal to pi squared over 12 minus Ahmed's integral. And now we have a system of equations, this first one, including Ahmed's integral, and this one right here, and we can plug stuff in and then we are done. That's a really long one, so elementary ways are way harder most of the time, or way more work than those sneaky Leibniz rule ways or something like this. So I've written everything out, kind of, and now all that's left is to evaluate this. I have done this before, so this right here should evaluate to the inverse tangent of x over square root x squared plus 2 from 1 to infinity. If we evaluate this at 1, well, this is just inverse tangent of 1 over square root of 3, should be pi over 6. So this is just pi over 6, negative. And now we have the inverse tangent of this stuff approaching infinity. The thing is, inverse tangent is continuous, should be, on this interval from 1 to infinity. That also means that we can bring this limit to the inside. So taking the limit as x approaches infinity of x over square root x squared plus 2. And the cool thing is we could just factor out an x squared, so this limit does exist. That's really cool. Factoring this out, we are on a positive interval. Absolute value of x is just going to be x in this case. So we have this limit right here, x over, and this is just x times 1 plus 2 over x squared. This is going to cancel out. If we take the limit, this is going to go to 0, so we have 1 in the limit. So we have the inverse tangent of 1, basically, which is pi over 4. We can advance this fraction by here to 12, for example. Yeah. Down here we have a 12 now, and this is also going to be a 12. So this is just pi over 12 times pi over 2 is pi squared over 24. So that also means that Ahmed is now nothing but pi squared over 16 minus pi squared over 24 plus this chunk, but this chunk is nothing but this right here. So plus pi squared over 12 minus Ahmed's integral. We can advance this by 2 over 2, getting rid of this chunk right here, leaving us just with this pi squared over 24. Now we can add Ahmed's integral on both sides. That's equivalent to saying that 2 times Ahmed is nothing but this right here. We can advance this to 69. So we have to multiply this by 6 right here. So 6 pi squared over 69 plus we have to have a 4 right here. So 4 pi squared over 69. In this case, that's a lot of arithmetic. I'm terribly sorry. Combining those gives us 10 times pi squared over 69. And now just dividing both sides by 2 because it's not equal to 0 leaves us with 5 times pi squared over 96. Oh, I said 69. I'm terribly sorry. I just love 69 so much. There was a lot of work. I hope this didn't feel rushed. It probably did. If you did enjoy this video, please like and subscribe and recommend the channel if you like. If you want to support the channel a bit more, link to my Patreon is in the description, or buy those t-shirts I created. And up until the next video, have an Ahmed day. See ya!
Mm.